Welcome everybody, I'm Professor G, and today what we're going to be talking about is we're going to be talking about the Copernican revolution, sometimes referred to as the scientific revolution. Either one's fine. So the Copernican revolution takes place in 17th century Europe. And it begins with a gentleman named Nicholas Copernicus. But before we get to Copernicus, let's talk about how people before Copernicus viewed the world and how they viewed the universe, what their cosmology was like. Cosmology being the study of the cosmos, not only of the planets and of the stars, but also of the earth and life on the earth, kind of asking questions: how did it get there? How do planets form? How did the stars form? These sorts of general questions. So let's deal with pre-Copernican cosmology. Now, pre-Copernican cosmology was deeply influenced by the Greek tradition, by the ancient Greeks, specifically two people. First of all, we have the Greek astronomer Ptolemy, who basically comes up with what's referred to as the Ptolemaic system, which has the Earth as the center of our solar system, a geocentric universe in which the planets and the sun and the stars revolve around the Earth. That's Ptolemy. And the second most important person in pre-Copernican astronomy is the Greek philosopher Aristotle. And Aristotle is important because Aristotle develops, so Ptolemy develops the geocentric universe. Aristotle explains how that universe works. Aristotle explained why we have motion, why things behave in the manner that they do, why the planets revolve around the Earth in the way that they do, and why, for example, if I throw this pin up in the air, why it moves in the manner it does, the speed at which it moves. Okay, now one of the defining characteristics of pre-Copernican astronomy, well, first of all, let me clarify some terms. Astronomy as we know it, astronomy being the study of the stars, the study of the universe, didn't exist until the 17th century. So I'm being a bit anachronistic here when I say pre-Copernican astronomy, because it wasn't really astronomy like we think of astronomy. Okay, it was more a mixture of modern astronomy and astrology. Don't get these words confused because they're very close in spelling and very close in how they sound, and some people kind of jumble them up a bit. Astronomy is also the study of the stars, and it's also the study of the planets, but astronomy holds to this idea that the movement of the stars and the movement of the planets somehow affects life on Earth. It affects life on Earth in terms of you and me, in terms of our personality, in terms of what's going to happen to us, in terms of our love interest, in terms of our whether or not we're going to have a good week or not, financially speaking. This is astrology. And an example of astrology that you're probably familiar with is your horoscope. Some people check these, they got like apps now, your daily horoscope, right? Horoscopes are a part of astrology, right? If you're born at a certain time of year, then you are a certain sign. I'm a Pisces, or I'm a Cancer, or whatever. And based on my sign is somehow going to determine my attitude. That's astrology. And pre-Copernican astronomy is a mixture of what we would consider astronomy, tracking the movements of the planets in some kind of quantitative way, and astrology, that the movements of the planets somehow impacted our day-to-day personal life. But also religiously. Pre-Copernican astronomy was deeply intertwined with religion, because most ancient people, the reason why they cared so much about the movements of the stars is because the stars and the planets were divine. On Earth, you have earthly creatures, you have us, nature, but out there is the heavens, is the gods, is the realm of the gods, right? So ancient people looked at the stars and looked up at the night sky in a much different way than we do today. And this explains why they were so interested in it. It wasn't just about calculating the motions of the planets, but it was about tracing the movements of the gods. It was about figuring out how and why these planets impacted us. So I just wanted to make that point kind of clear there. So let's talk about the pre-Copernican worldview, or pre-Copernican cosmology. Now, pre-Copernican cosmology is sometimes classified as, the historian of science Thomas Kuhn called it, a two-sphere model. A two-sphere model in which you have the earthly sphere, the Earth, at the center of the universe. And around the Earth, you have the movements of other planets, such as Mars, Venus, the Sun. Okay, so these are the planets that are moving around the Earth. And the outermost sphere, the outermost circle, is the realm of the fixed stars. The realm of the fixed stars. These are the stars that you see in the night sky that don't move, right? So if you were to go out tonight and look at the night sky, and if you paid close enough attention, you would notice that some stars move. They rotate in a predictable manner. Those are planets. But if you stared long enough and hard enough for a consistent amount of time, you would notice that a majority of the stars don't move. And so this is what they called the realm of the fixed stars, that there was an outermost sphere to our universe that didn't move, that it just stayed put. Now, today we know that the reason why they stay put is because they're so far away and we can't actually see them moving. But for the ancients, this is the two-sphere model with the Earth at the center of the universe, the planets revolving around the Earth, the sun revolving around the Earth, and the realm of the fixed stars. And this is basically at the heart of the Ptolemaic system. The Ptolemaic system. Now, this begins to change. Begins to change before Copernicus. Certain Arab astronomers in the Middle Ages started to notice that there were some inconsistencies with the Ptolemaic system. Notice that the planets didn't always behave in a predictable manner. That sometimes the planets, the belief was in the Ptolemaic system that the planets moved in a perfect circle. Well, sometimes these astronomers noticed that they didn't. And this leads to a series of problems that is sort of building up to Copernicus establishing his view. So one of the central problems is known as retrograde motion. Retrograde motion. So this is going to be you. And there's a reason why I flunked art class. It's because I'm no good. So this is you here. And you're staring up at the night sky. And let's say you're tracking the motion of a planet. And so from your perspective, it's going to move in basically half of a circle around you from your perspective. Now, what these pre-Copernican astronomers and what Copernicus himself, the problem that they were trying to deal with is the fact that planets don't move in a perfect circle. Sometimes when you're staring at them, okay, so this is a planet here that's going to be moving. Sometimes this planet along its course will start to go forward, and then all of a sudden it starts to go backwards, and then all of a sudden it goes forward again. That if you track the motions of the planets, sometimes they go back in the night sky. They're headed on one course, they go back, and then they go back again. And so the problem was trying to figure out what was happening here. What was the issue? Why did the planets behave in that way? And the solution to this under the Ptolemaic system was the epicycle. The epicycle. Basically, an epicycle is a small circle within a circle. All right, so let's go back to our moving planet here. An epicycle would be your planet is going along its course and it hits an epicycle. The planet's going along the course, it hits this, it goes in a circle, and then it continues back along its course. And this explains retrograde motion. This explains why the planet goes backwards in the night sky and then goes forwards again, because it hits a small epicycle. Now the problem is that this is a very simplistic picture, right? And the problem is that there had to be more than one epicycle because planets did this multiple times, right? And so the problem with the Ptolemaic system is it becomes increasingly complicated. You start to have epicycle on epicycle on epicycle. You start to add all these epicycles together. But this is an important point here. It's not to say that Ptolemy was wrong. Okay? Mathematically, this can still work. You can still calculate the positions of the planets. The genius of Copernicus lies not with proving Ptolemy wrong, but with simplifying the math. Copernicus says it would make much more sense if instead of the planets and the stars revolving around the Earth, that if we had the planets and the stars revolve around the sun. A view that became known as heliocentrism. Heliocentrism, the view that the sun is the middle of our solar system. And this is what Copernicus proposes. Also of note, Copernicus proposes this mathematically. Copernicus couldn't actually observe this. Okay, this is one of the things we're taught that's a fundamental aspect of science nowadays. Is supposed to be observation. You observe the data and then you base your you base your hypothesis off that data. There's no observation here. Copernicus has no physical proof that this is true. Rather, he has mathematical elegance on his side. His equations are more elegant, meaning they're more simplistic. They provide a simpler understanding of how the universe operates. So Copernicus publishes his results. His ideas are, people understand why he would propose it mathematically, but he's not very popular. It's not to say that people didn't like Copernicus. Historically speaking, it's just that people didn't really read Copernicus. It wasn't very popular work. The great popularizer of Copernican theory is going to be two men, Johannes Kepler and Galileo Galilei. And it's going to be Galileo that's really the spokesperson, kind of Copernicus's bulldog. He's going to be the spokesperson to bring this into public conversation and public debate. But there's going to be some complications here, not just over the mathematics, but over how we view the universe and what it means that Copernicus is right. Because Galileo is going to bump up against some people who disagree with him. Probably what you have in mind is Galileo's confrontation with the church. But it's not just his confrontation with the church. It's not just whether or not this disagrees with the Bible or with the Holy Scriptures. It's about this conflicts with their basic understanding of science. All right? What Copernicus is going to say, and what Galileo is going to take up, is that his theory, the Copernican theory, the heliocentric model of the universe, is based on mathematics, as we said before. What Copernicus is going to argue, that's going to kind of rattle people's cages, is that this mathematics is not only true because the calculations are true, but that the universe is inherently mathematical. That if we can prove something through mathematics, it must be physically true. And this is what the historian John Henry calls the mathematicalization of the world. The idea that physical reality could be explained through mathematics. And this is an idea that was very new. It's an idea, this is why Copernicus is so important, this is why Galileo is so important, is the idea that physical reality could be explained through mathematics. In fact, Galileo is going to say that the universe is coded with mathematics. In much the same way, if any of you are experienced with computer coding, right, you go to a web page, that web page is really just code. It's a series of letters and numbers comprised, put together by a web page developer. They put it together and it comes out looking like this beautiful web page. The exact same thing is happening here, that the universe is built on mathematics, but what we see is the result of that. And so this is really the beginning of modern science. And what we're going to see here is a shift to a more, not necessarily empirical, but a more quantitative understanding of reality, in a want, in a desire to be able to explain phenomena, to be able to explain what we observe in the world quantitatively through mathematics. All right, folks, hope this video helped. Email me if you have any questions, and I'll see you guys later.